Hey guys, this is a submission for Machine Learning Foundations for Product Management course on Coursera. So the project is about to build a model that predicts electrical energy output, uh, which uses a combination of different features. There is an observation set. This data set has a bunch of, not a bunch, but like let's say four features and one outcome and target feature that we are trying to predict using uh, the models, and the data set is available. So I'm sure everyone who is going to be reviewing this assignment already aware about this data set. So to attack this project, we're gonna have like an implementation plan. We're gonna have an approach which would consist of figuring out what kind of algorithm and model we should be building, how we're gonna build this model, and basically a summary or interpretation why we're selecting one particular model. High level details, so not to dive into the woods, given uh, the project obvious selection is going to be a linear regression. We're going to be building three models that we're going to evaluate using the mean squared error metric and mean absolute error metric. We're going to add some caveat to that, which I'm going to explain while presenting the models, and during the interpretation step or on the summary, I'm going to explain why the particular model was selected. So without further ado, let's just dive into the model building using linear regression approach. So, as I said, what we're gonna be doing, we're gonna try to implement our first model. In this model, we're gonna be using all of the four features that are available in our observation data set. Our observation data set is gonna be split into three uh, subsets. So our training data sets, which is approximately 80% of the initial data set, the validation data set is a subset of training data set that represents probably like 20% of it, and a test data set which is not present neither in the training or validation observation data set that is about 20% of each. And we're going to be using the same approach for each of the models that we are experimenting with. So the first point of attack is what we are doing here. We are figuring out the correlation for each of the features with the target feature. And for that matter, we're using a correlation function in the Google spreadsheets. And for the first model, we're gonna be doing really straightforward approach, which would mean that the correlation is going to be used as a coefficient parameter for each of the features. So basically, like the correlation of 0.95 is going to be used for AT, 0.87 is going to be used for V, and so on and so forth. Using this approach, one little thing that I need to explain is like I'm adding a bias to our uh, predicted value of PE uh, with the hypothesis that each of the features have the same value, and meaning that like feature of AT gonna have like can contribute like 10 to the bias, same for V, AP, and RH. Uh, for our outcome metrics or like our validation metrics, we're going to be calculating the ABC and MAE for each of the observations, and basically we're going to be using that in the validation. I also created some visuals or charts just to show how visually our prediction using this model aligns with the actual values that are available in the dataset. So we're gonna be doing the linear regression for training, validation, and test datasets, and calculating our outcome metrics. And as I said, we're gonna add some caveat to that. So we are not gonna be sticking to the usual sum approach, which is kind of shown over here, but we're gonna be averaging it, and I mostly prefer the absolute approach. That's why I like as the final validation metric, I'm gonna be using the average of the MAE. So as you can see, this is our metric that we're going to be using in the interpretation step. The second model uh, that I wanted to try is basically not rely on the correlation values for each of the features, but basically try to fine tuning it on my own, and so I can minimize the cost function of MAE and MSE. It took a little bit of work, but basically I was happy with the result, and the outcome metric that I managed to succeed is shown over here. And the third model, which uses the same algorithm and the same approach, but it had I decided to get rid of one of the features just to test and to see whether or not it makes sense, is model 3, where I got rid of the RH feature, and it was pretty easy to do, just like adjusting the coefficient value of this feature using all of the formulas that already were available here. So by setting it to 0 and coefficient values for other features, I just decided to use the correlation value. So doing the same analysis, the overall outcome metric looks like this. Now let's dive into the interpretation step or summary. For the simplicity, I just took all of these summary uh, numbers from each of the models that we got in the previous step and basically put them in the separate sheet. Uh, the obvious or intentional God would tell one person that we should go with the model number one, right? It had like the good outcome metric, the lowest outcome metric on the training set. It had the lowest outcome metric on the validation set. It, but something is weird over here, right? It basically says that during the tasting state, or you can think of that as like new data coming in, this model is not performing as good as it might would assume, or one would assume based on like training and validation. Our model number two is performing better on the testing stage. It kind of doesn't look good on training and validation, uh, which is again like a weird observation. And then like we have the model number three, which didn't perform that well on the training. It did a significant improvement on the validation thing, and during the testing, it it performed really well. So it made me think, and I created this chart just to outline how things are going with the models being created. And as you can see, model number three has a greenish background, which means like I selected as a winner model. And the reasoning behind that is model number three not only has R square, the highest R square possible, it also has best trending line for it, and it performs better for the new data, which is basically the purpose of the project, to be able to predict the PE as accurately as possible. So thank you so much for looking into that. I hope you all guys have a great day, and hopefully we'll see you in the next course.